Okay, thank you very much. So, first of all, I would like to thank the thesis committee for being here and accepting to evaluate my work. So, I will present it. It's about theory and algorithms for learning metrics with a controlled behavior. So, let me start with a little bit of context. It's a thesis in machine learning. Sorry. Okay, so it's a thesis in machine learning, so which is a field of artificial intelligence. The idea is to acquire automatically new knowledge from data. So, for example, you have a set of examples, blue dots and red dots, and the goal is to learn a classifier such that all the examples on the left are blue and all the examples on the right are red. This is called supervised learning because we have access to the labels of the examples beforehand. But there is other kind of paradigms in machine learning. So, for example, unsupervised learning, where the idea is that you do not have access to the labels, and the goal is to group the examples together such that they share some meaningful properties. Machine learning has been used in a wide range of applications. So, for example, in image classifications, assume that you have some images of rabbits and squirrels, and the goal is to learn a classifier such that when you have a new image, you are able to tell if it's one animal or another. Another kind of application is, for example, image segmentation, where what you want is to obtain groups of meaningful meaningful objects in the image. So you want to identify the birds or the walls in images. A third example is tracking of images in videos, where the idea is that you have some frames from a video and you have the bounding box of one object, and what you want to do is to track this object throughout the whole sequence. To perform such task, you need a good representation of the object. Indeed, many machine learning algorithms use, in fact, a numerical representation of images or videos, and the idea behind representation learning is to automatically learn this representation from the data. So, to give you an example, you have an image, you perform a task of representation learning, so for example using deep learning, kernel learning, metric learning, and you obtain a d-dimensional numerical vector that you can use to perform classification or other tasks. This is often a key property in machine learning, and this thesis will be particularly interested in metric learning, which comes from the fact that many algorithms critically depend on a notion of a metric, on a notion of comparisons between objects. For example, the nearest neighbor classifier is an algorithm to classify the examples with respect to their distance. So, for example, if we want to classify the black dot, we'll look at all the nearest examples and say, okay, the closest one will give its label, so in this case, it's blue. Now, imagine that, in fact, we know that this example should be red. We have a problem because if we look at the nearest example, the label is wrong. What we would want would be a space like that, where all the red dots are close to each other and the blue dots are far. Obtaining such a space can be difficult if we try to learn it, to design it manually. So the idea behind metric learning is to automatically learn from the examples by imposing some constraints, which are to bring closer similar examples and push far away dissimilar ones. So the goal is to obtain this space after optimizing a problem. And we'll see in more detail that. So for this presentation, I will start with a little bit of background, and I will develop two contributions of this thesis. The first one try to control the behavior of metric using side information, while the second one try to control the underlying transformation. And then I will conclude with and give some perspective on this work. So to start with the background, so this is a thesis in machine learning, and more precisely, we are mainly interested in supervised learning problems, as the examples that I gave in the beginning with blue dots and red dots. The idea in supervised learning is that you have access to a space, a d-dimensional space, which corresponds to the numerical space of the examples, and a label space. So, for example, in a binary classification, -1 and +1. We also assume that the problem that we want to solve is entirely defined by a distribution dt, but we also assume that this distribution is unknown and that we have only access to it through a training set T of limited size. The fourth assumption is that we know an hypothesis set. We have an hypothesis set of models that we can use to solve the problem, and we have access to a loss function L, which give an evaluation of a given model on a given example. What we want is to minimize the expected risk to find the hypothesis with the minimum expected risk on the whole distribution. But the problem is that we do not have access to this true risk because we don't know the distribution. What we can do instead is use the empirical risk, which corresponds to the average error on the training set. And we can optimize this value to obtain a good hypothesis. However, one must be careful to not fall in a problem of overfitting where the hypothesis is good on the training set, but not on new examples. So the hypothesis can't generalize. So to overcome this problem, one way is to use regularized risk minimization, where the idea is still to minimize empirical risk, but we add a complexity term which limits the kind of hypotheses that are usable. So to illustrate the problem of overfitting, it's the idea that we have a very high complexity and a very low empirical risk on the training set, and we are now of generalizing that to new examples. Another problem that may arise is that if we have an hypothesis which is too simple, the empirical risk will be very high, and we can generalize it. Now, a question is, how can we evaluate the generalization ability of an hypothesis? One way to do that is to use theoretical frameworks that build upon the pack learning framework, where the idea is to derive generalization bound, which says that the true risk is bounded above by the empirical risk, plus a term that we want to be small and to tend to 0. These bounds should hold with high probability. The idea behind this term is often that it decreases with the number of examples, and that it increases with the complexity of the hypothesis space. Now that we have defined the supervised learning setting, we can switch our attention to the problem of metric learning. So first, let me define what is a metric. For us, in this thesis, a metric is any pairwise function, so it takes two examples in parameters and returns a value. So some examples are, for example, the Mahalanobis distance, which is parameterized by a matrix M. The Mahalanobis distance can be seen to correspond to a linear transformation of the input space such that some constraints are respected through the matrix L. Another example is the bilinear similarity, which is also parameterized by a matrix M. And a last example is to learn multiple metrics across the space to obtain some nonlinearity on the problem. So let me give you, now that I have defined what is a metric and what kind of metric we can learn, we need a loss function to perform regularized risk minimization. So one kind of loss can be as follows. We return an error when similar examples are too far from each other, so with respect to a margin gamma c, and when dissimilar examples are too close to each other with respect to a second margin gamma dis. And if the examples are well spaced in the space, then we return no error. So now we can define our optimization problem, where the idea is to minimize the error on the similar examples and the error on the dissimilar examples, and we still add a term of complexity to not obtain too complex metrics. So a typical workflow for metric learning is then to have the input space. We find some constraints between the examples. So similarity constraints and dissimilarity constraints. And then using metric learning, we can obtain a new space where the task that we want to solve is easier. So to give you a brief overview of the state of the art in metric learning, we can answer 4 different questions. So first, what kind of metrics can we learn? How can we learn these metrics in practice? Can we derive some guarantees on these metrics? And what kind of tasks can we solve? So to give you an idea, in this thesis we are mainly interested in man-on-list distance metrics, but we also perform multi-metrics learning in one of our contributions. We usually use risk minimization to learn the metric. We derive some generalization guarantees, and our applications are mainly classification and domain adaptation. So now that we have seen a little brief overview of the state of the art, we identified several drawbacks in metric learning. The first one is that many approaches have been proposed and shown to work well empirically, but they often lack some theoretical results to justify them. Furthermore, the control over the metric is often limited or, let's say, poorly analyzed. So what we propose in this thesis is to learn some metrics with a controlled behavior. And to do that, we propose 2 main settings. The first one where we use some side information, and the second one where we explicitly control the underlying transformation of a man-on-list distance. We propose 4 contributions in this thesis. In the first set of contribution is with local control, where the idea is to control either the metric for each pair of examples or each example individually, or some more global control on the metric or the transformation. I won't detail the contribution in local control, just give you a brief overview, and I will go in more length for the problem of global control. So let me start with the problem of local metric learning for perceptual color differences. The question is to approximate distances between colors. So for example, you have 2 patches, 2 green patches, and you can't see the difference. And you have a blue patches and a purple patches, and you can see the difference. But in the color space where they are extracted, they have the same distance in practice, and they do not reflect the human perception of colors. So our goal is to learn a new space where this human perception is respected. So we propose a solution where we regress the values of malanoid distance. We use local metric learning to add some non-linearity, and we propose some generalization guarantees for the learned metrics. And to give you an idea of what we learned, here is the RGB cube with some ellipses, which represents the distance between one point and all the examples at a distance of 1. And you can see that local metric learning is useful because we have very different shapes in different parts of the space. And we use the learned metric in an application of segmentation. And we can see that it helps. For example, in this image, we are able to retrieve the pot, while it's not the case in the state of the art, here and here. Here, the idea is that we retrieve the sun, while the other approach can't. So the second the second contribution that I will present is regressive virtual metric learning, where the question is to control the underlying transformation by moving the example in the space. So we propose to regress virtual points. So the idea is that instead of using similarity and dissimilarity constraints, we define some virtual point and we associate the examples to these virtual points, and we just minimize the distance between the example and the virtual point. So we propose once again some guarantees and some links with pair-based metric learning approaches. And we'll see in the next slide that we are able to induce some specific properties on the metric, in particular in classification. So in this example, we are able to learn a metric which, for each feature, separate one class from the other. So here are the blue dots, the green dots, and here are the blue dots. And it's a good way to improve the problem of classification. So now that I presented the problem of locally control a metric, I will present in more length the problem of globally control this metric. So I will present two contributions. The first one where the idea is to use some side information, and the second one where the idea is to follow a geometrical transformation which is implied by optimal transport. So let me start by the first contribution, which is metric hypothesis transfer learning, where the problem is to say many algorithms have shown that using some side information can be interesting in solving metric learning problem, but there is no theoretical analysis of this interest. So what we propose is to analyze a framework that I will present in the next slide, and to derive some goodness measures on the metrics, which allows us to analyze their interest in the problem, for the problem. So let me introduce the framework. We consider regularized metric learning, risk minimization for metric learning, where we minimize empirical risk, once again, plus a term of regularization. So let us consider that we have this data as input. In fact, the regularization term can be seen as a term which biases the metric toward 0. In other words, we are trying to learn a metric which is as close as possible to the metric which collapses all the examples in 0. So if it's a classification task, it's not a good idea because we can't do anything in this space. It makes the problem harder. Instead, we could consider, for example, the initial space by considering the Euclidean distance, or we could consider another metrics such as the Mahalanobis distance, the original definition, which use the variance-covariance metric matrix of the examples, and which is well suited for classification also, and which could help for the problem, to solve the problem. We propose three kinds of theoretical analyses, and I will detail two. The first one is use uniform stability, while the second one is based on the Rademacher complexity framework. And the goal is to derive some goodness measures on the metrics, and to understand the interest of using a source metric to help during the learning task. So to give you some intuition about uniform stability, the idea is to say that small changes in the training set should not change the output too much. The uniform stability depends on the number of examples, so it means that if we have less examples, we allow bigger changes than if we have more examples, where changing one example by another will not change the output much. And using uniform stability and making some assumption on the loss function and the regularization term, we can derive some generalization bounds. So these assumptions are positivity, convexity, Lipschitz-nets, and sigma m admissibility. And we have to only consider the Frobenius norm as the regularization term. For the regularization, the generalization bound, we obtain the standard results. These standard results where the true risk is bounded by the empirical risk plus a term which depends on the uniform stability and a term which depends on uniform stability and sigma m admissibility. In this case, we do not have any information on the source metric yet. So what we want to do is to modify the proof technique to obtain more information. And in particular, we consider a specific loss. And we are able to see that we can introduce a kind of regularized risk of the source metric in the bound. And it gives us a first measure of goodness, which is the empirical risk of the source metric on the training set, plus a term which measures the complexity. So the problem of this framework is that it is limited to it's limited in the kind of loss functions that we can use, and it's also limited to only the Frobenius norm regularization term. So to overcome this problem, we propose a second approach, a second analysis based on the Rademacher complexity, where the idea is to say, instead of only studying the training set and a small modification of this training set as in uniform stability, we will evaluate the complexity of the metric class in its entirety by evaluating the ability of the hypothesis at fitting a random noise. Once again, we are able to derive some generalization bound under weaker assumptions. And in particular, we only require that the regularization term has a well-defined dual norm. So this generalization bound can be shown to depend on the source metric in a way that is the worst possible error of the source on the whole distribution. And this is an interesting move because the Rademacher complexity can be shown to depend also on the source metric. So it means that if we have a reference metric which is perfect for the problem at hand, then the bound is vanishing in the sense that all this part goes to zero, and it shows that learning is not necessary anymore because we already have the best source. Let me now compare the two bounds with each other. So, in particular, we have the goodness of the source metric, which is in one case empirical, which means that it depends on the training set, on the complexity, and it can be computed in practice, while the other goodness is theoretical, in the sense that it cannot be computed in practice, and it's harder to use in an application. However, the Rademacher complexity is interesting because it gives a vanishing bound. So we know that if we have a perfect source metric, then there is no need to learn. And it's applicable to a wider range of regularization terms. Let me show you some experiments to demonstrate the interest of the two bounds. So first, choosing a good source metric with the empirical measure of goodness that we derive, we propose to reweight the source metric to improve the tightness of the bound, and we can show that on several dataset, UCI dataset, it in fact also improves the quality of the learned metric. And to show you the interest of the Rademacher complexity, we can use it with various regularization terms, which will imply different behavior on the closeness between the source metric and the learned metric. Let me now conclude. So we proposed a framework for metric hypothesis transfer learning with biased regularization. We proposed several kinds of theoretical analysis, and what I did not present here is that there is a third analysis with a third measure of goodness, and that we also demonstrated the interest of the approach on a transfer learning task. Some perspective of this work are to obtain a vanishing bound with empirical goodness, and in particular a fast rate bound. So, which is to say, if the goodness is empirical and the bound is vanishing, then we can use it in practice to select the best source metric in a set. So we have seen one way to globally control the metric using some side information. So now I will switch to the second contribution that I will present, which is about controlling the underlying transformation of the metric. So for that, what we propose is to learn a metric which follows the underlying transformation of learned by an optimal transport problem. Our solution is based on an optimization problem where we minimize the difference between the optimal transport transformation and another transformation, and I will present it later. And we'll show that there is some application in domain adaptation and also in image editing. But first, let me give you a brief introduction to optimal transport. So the idea behind discrete optimal transport is to bring closer some distribution and some set while preserving their mass. So for example, we have the green dots and the red dots, and we want to bring the two closer. So what we want to obtain is these results at the end. And to do that, what we will do is that we propose to learn optimal transport, propose to learn a coupling, which is a matrix which associates each source example to some target examples, while preserving the masses of the examples to obtain a good result. So a bit of formalism, some notations. We consider this time that we have two spaces, the source space and the target space, which can have different size. Once again, we consider that we have two probability distributions which entirely define the problem, but we do not have access to them, and we use some training sets as a proxy. We also have a cost function, which is the cost of moving one example from the source to the target. And to learn the coupling matrix, we can use control-rich formulation, where the idea is to minimize the product between the coupling and the cost matrix. Once we have computed this coupling, the next question is how can we move the examples in practice? To do that, we can use value-centric mapping, where the idea is to say, okay, if one source example is associated to 3 different target examples, then we'll move this example to the very center of the 3 target examples. The problem with this approach is that we cannot perform out-sample computations because we do not have any information about the coupling for new examples. So instead, what we propose in this work is to learn a transformation which approximates this value-centric mapping. For that, we use the following formulation, where the idea is to jointly learn the coupling and the transformation. So we minimize the difference between the transformation and the coupling to have them as close as possible for the training sets. We also minimize the cost of the coupling, so the cost of transporting the examples from the source to the target. And we add a regularization term to learn transformations which are not too complex. And this formulation can have 2 different interpretations. The first one is that we are solving an optimal transport problem regularized by a transformation, which is a transformation F here. But it can also be seen as learning a transformation which follows the result of optimal transport. Okay, so now that we have defined the optimization problem, we need to consider some transformation, and we consider 2 kinds of transformation, some linear transformations and some nonlinear transformations. So for example, if we have this data, so the green dots, and we want to bring them close to the orange dots, using a linear transformation, we will regularize the transport, and all the examples will move almost in a line. On the other hand, using nonlinear transformation, we are able to let more degree of freedom to the transport, and we can learn more complex transformation, and we can well move the example towards the others. And using our transformation, we can move out of samples examples in red here, and we can see that we generalize well because the arrows follows the trend of the training set. See here and here for the nonlinear transformation. We also propose a theoretical discussion. We have the problem of optimizing the formulation, where the idea is to jointly learn the transformation and the coupling. So, since our problem is jointly convex, we propose to use an alternate solution where we fix the matrix, the transformation matrix, and we learn the coupling. And in the other case, then we fix the coupling and we learn the transformation. And we repeat these 2 steps until convergence. One important thing is to note that when L is fixed, then the problem is convex with respect to gamma, so we'll converge. And this is the same thing for gamma fixed. We also have a convex problem, and we also converge for L. So now let me present some theoretical discussion on what we learn. And we consider the learned transformation and the theoretical transformation. And the idea is to say, okay, are we learning a transformation which is close to the true transformation, so which has a small estimation error. And we can show that this estimation error is bounded by the approximation error, which is the difference between the learned transformation and the learned barycentric mapping. So this is exactly what we minimize in our problem. The second value is the barycentric estimation error, which is the difference between the learned barycentric mapping and the true barycentric mapping. And we expect this value to be small as n increases, because it means that we can well approximate the barycentric mapping with a set of examples. And the last value is the barycentric approximation error, which is the difference between the theoretical barycentric mapping and the theoretical transformations that we could obtain if we had access to all the examples. And we also expect this value to be small because it's a way to evaluate the goodness of the barycentric mapping for the problem of optimal transport, for estimating the transformation of optimal transport. We show some application of our method in two kind of experiments. The first one is domain adaptation, and the second one is image editing. The idea behind domain adaptation is that we have access of a source and to a source and a target, but the two domains are related but different, in the sense, for example, here that we want to classify the same kind of object, but in one domain we have the object on a white background, while in the other domain we have the object in the white. And we can't use directly the classifier learned on the source and the target because it will not give good enough results, because we need to overcome the drift that appears between the distributions, the difference between the source and target distribution. So what we propose is to use optimal transport to bring the source and target distribution close to each other, and then we can use a classifier learned on the source and the target. So we propose to use our approach on domain adaptation on two datasets, the Moons dataset and the Office Caltech dataset. So first, on the three examples, which is the Moons, where the difference between the source and the target, so the source in blue and red and the target is black, is that there is a rotation, in this case, of 40 degrees. We can see that in both that our approach is able to overcome the difference between the two domains, but using a linear transformation is slightly more interesting because it's closer to our rotation, and we more closely follow the target when we project the source. In the nonlinear case, we see that we give more freedom to the problem of optimal transport, and in particular, we try to bring the source example toward a place that we do not want, and they do not follow as closely the target. A second application is the Office Caltech dataset, where we have 4 different domains, and the difference between the domains is, for example, the example that the images are taken on a white background, or in the white, or with poor quality cameras. In this case, we compare our approach on the right to several state-of-the-art approach which also use optimal transport. And what we can see is that we obtain better results because our approach is able to regularize well the optimal transport problem and to force it to obtain meaningful transformation between the source and the target. We also propose some experiments in image editing, where the idea is that we have a source image, a target image, and we want to move a part of the source image, for example the face, to the target image in a seamless fashion. The state of the art is in the middle, and our approach with linear transformation or kernelized transformation is on the right. And we can see, for example, here that we obtain better results because we are able to forget about the colors, while the state of the art still has some pink on the face. In the second case, we can see the interest of using more complex transformations, because if we use a linear transformation, we have a kind of blur over the image because the shift is quite high, while using kernelized transformation, we have something which is far better. And in the last image, we can once again see the interest of our approach because we are able to obtain colors which are closer in spirit to the image, to the target image. So to conclude, we propose to learn a transformation which is associated with a geometrical transformation, which comes from the problem of optimal transport. And we apply our method in several tasks, such as domain adaptation and image editing. Some perspective will be to further extend the theoretical study. In particular, the idea behind generalization of the barycentric mapping. But we can see that our method will allow us to use optimal transport in new problems, in particular problems where out of samples computation are mandatory. So now let me conclude this presentation with a brief recall of what we saw, that the control of the metric can be local or global, that it can be done using a reference metric, either an unknown reference metric or a non-reference metric, or using other means and controlling the transformation, either using some virtual points or a geometrical transformation, which comes from optimal transport, for example. To give some perspectives on this work, we can offer some theoretical guarantees. It would be interesting to offer some theoretical guarantees on the algorithms that make use of the learned metrics. So the idea is, for example, in a classification problem, it would be interesting to theoretically study the impact of a well-controlled metric on the results of the algorithm. Similarly, in a domain adaptation problem, it could be interesting to derive a bound where the risk on the target is bounded by the risk on the source, plus a term which depends on the control metric, on the metric that is learned. Other perspectives are some research direction for the concept presented in this thesis. In particular, using control metric in online learning. For example, if we are able to detect some drift in the stream of examples, it would be interesting to automatically adapt the kind of control that we apply on the metric to enhance the goodness. In active learning, the idea would be to query some meaningful points to verify that we are correctly controlling the metric and adapt it if needed. And in deep learning, we could consider, for example, using a transformation, a control transformation as a new kind of layer, in particular when we are using optimal transport. So thank you for your attention.